So hello and welcome to Chapter 11, our chapter on the muscular system. There are several things about the muscular system that are overview type statements that you have to keep in your head at every moment. So if you check those overview type statements, they'll identify your mistakes in many cases. Remember that a muscle, just learned this in Chapter 10, can only contract. That means the only thing it can do on purpose is pull. In a way, it's sort of like a rope. You put a rope on something, you can hold something, and you can pull it towards you. But pushing on a rope actually does you no good. So how is it we have so many bodily movements? When I sit here and move something, like I flex my elbow and I extend my elbow, it looks like I'm pushing and pulling that joint. And in fact, that's intuitively attractive. But in fact, what's happening is muscles are arranged around that joint. On the hinge, since the motion is mainly in this anterior-posterior plane in the anatomical position, that means that they're crossing the joint on the anterior surface and on the posterior surface. So the muscles on the anterior side flex, and then they relax, and the muscles on the posterior side of the humerus extend the joint. So back and forth really represents two very different and opposing sets of muscles that accomplish those two movements. Now, we can find out that the elbow does have a few more variations. There's also a rotation that's possible at the elbow. The radius and its head on the capitulum of the humerus allows that rotation, but when we do that rotation, what we do is we actually cross the radius over the ulna, and it flips the hand over, pronates the hand. These different shapes, though, are kind of a manifestation of the idea that muscle fibers are strings. The fibers within the fascicles and the fascicles within the muscle itself are basically designed to pull in a straight line. So if you want different angles of tension across the joint, then you have to fan those muscle fibers out into a different shape. So what we'll see as a convergent muscle is built kind of like a fan. It always pulls on the same point, but it can pull directly, basically pulling them in this direction, or it can pull from the other side, pulling it in this direction. And that affects how something as mobile as a ball and socket joint can provide so many movements. Joint movement is going to be influenced by the differences in the mechanical properties of that joint. There's going to be a load, a weight, a force, and there's going to be a fulcrum, a place where the joint is pivoting in some way as the articular surfaces slide on one another. So what I want you to do for this system, I'll put it right here in the first slide. Know the names of the superficial muscles that we will look at. Those muscles are listed in good form on slides 12 through 16 of this presentation, but the figures in the text are equally useful. Plus, section number 2, a detailed information of the list of 10 muscles, and I'll try to point those out as we go through the lecture and look at selected figures and slides that reveal the muscles and their attachments. So let's first talk about shape. When we talk about a muscle, we'll notice that it has a large red central portion. This is where the sarcomeres make up the myofibrils, and they're bundled into fibers, and fibers are bundled into fascicles. When you cut across the whole muscle, you can see these bundles called fascicles. You can see them with the naked eye. But down below those, the fibers and the myofibrils enter into the microscopic realm. Now, if you try to pile a whole bunch of muscles up together in a straight line, you get this bulge in the center, and that's quite all right. This is called a parallel muscle, so even though there's a little bit of an angle, it's a straight muscle, basically, because it attaches up here and attaches down here, and it's going to pull straight along that axis. So the red or contractile part of the muscle we call the body or the belly of the muscle. You can see this particular cross section would have the epimysium out here and the paramysium around the fascicles, and you can just barely see the divisions of what's called the endomysium around the fibers. So what we have here is a parallel muscle, the biceps brachii, designed to pull in a straight line. And it's a fairly large muscle. Flexing the elbow is really a pretty important job, given how much we use our hands and our arms. So, first muscle is a parallel shape. This one you can see is a fan shape. Notice also that instead of being sort of round in cross section, it's very flat. This muscle is the Pectoralis Major, which lies here on the anterior surface in the mammary region of the thorax. Now, the attachment points, the base of the muscle that form the origin, are attached from up here. The clavicle has a bit of attachment, and it transfers over to the sternum, basically the costal cartilages, all the way down here. And it basically, as it curves around to this base, you see an attachment to the costal cartilages and even the margins of some of the bony ribs. So this fan-shaped muscle converges on this tendon, which is going to, in this case, cross the axillary region and attach to the humerus. So since it's attached on this side, it's basically going to pull the humerus in this direction. But this is a ball and socket joint. So we use it in a kind of an interesting way. No matter the position of our arm up and down, if we move our arm back, I would say it's cocking the arm. When I push this way, when I flex this shoulder, move it in this direction, it's the pectoralis major that's pulling that humerus around in that motion. A convergent muscle allows for some fibers to pull directly on the tendon, no matter the way you orient it. When you think about moving your humerus forward, you may start with it low and want to move it in an upward direction. That's where the upper fibers are pulling directly. Conversely, if you have it here and you want to push down as you flex the elbow, flex the shoulder, that's where the lower packets are going to be most useful and most direct in delivering force. But a lot of the time, you don't need a great big muscle. Every muscle isn't the biceps brachii. And in addition, there's so many different joints that you're trying to motivate that if you put just a bunch of straight muscles, they basically would interfere with each other, and the bulge of the muscle would restrict the dexterity of the joints. And so you see this kind of sideways displacement. Here's an extended tendon. It may go way down here off the screen in order to attach to the part that moves. But when you get up to the body of the muscle, you'll notice these are set at an angle. It kind of looks like a feather, so it's named unipennate muscle. The extensor digitorum muscle is a good example of a unipennate muscle. It sits here on the posterior surface of the lower arm, the forearm, and it's going to extend the fingers. So I can flex my fingers. That would be a flexor digitorum. And when I extend my fingers, I'm contracting actually a group of muscles that are up here and connected by long tendons. You can see those tendons on the back of your hand, all the way down here to a posterior connection on the phalanges of each finger. The extensor digitorum is a unipennate muscle, and they can be packed side by side, and the extended tendons actually take up very little space. A bipennate has a central tendon running up and down the center part of the muscle, and you'll notice that the bodies of the muscle here are angled in a different way. But when they contract, they're basically going to pull this bottom tendon, in this case. Oops, sorry, not this case. Yes, this case. Pull this tendon in an upward direction, kind of straight up. This is the Rectus Femoris muscle, and it's bipennate because it has one of these double structures that look feather-like around a central tendon. The Rectus Femoris is that muscle that's right on the anterior surface of your thigh. It is one of the quadriceps group, so its connection is up here on the top of the femur and the pelvis. But there are three other muscles, the vastus medialis, the vastus lateralis, and underneath it, the vastus medius, that form four different attachments on the humerus. This muscle is there to extend the knee. It's a pretty big muscle on the front of the thigh. Now, the flexors for the knee are around on the back of the thigh. And when we talk about the power behind our step, what's pushing us forward when we're walking on that leg, doing a power stroke on the right leg, it's the right leg flexors, the hamstrings, that are actually providing that propulsion. But as we put our left foot down and our right foot comes up, it's equally important to get our left foot forward, our right foot forward, and position our foot to catch us as we complete the step with the left. And that's what this rectus femoris does. Rectus means straight, and femoris tells you right where it's located, right on the top of the femur. Its job, extend the knee, and it's a bipennate muscle. From there, we find a repetition of that pennate structure, and nothing illustrates that any better than the deltoid. It's drawn in this way. You can see it has a kind of a convergent overall shape. And up here, this part of the muscle is wrapping around and running kind of perpendicular to the paper as it follows the spine of the scapula. And this is bridging the acromion of the scapula over to the clavicle and wraps around in the front to follow the clavicle. So this is a big U-shaped connection up here. And because of that U-shaped connection, it has a complex action. All three of these packets, anterior, central, and posterior, can act to abduct the shoulder. And let me just show you that once more. Because it runs over the top of the joint, abduct the humerus is its principal action. All three parts of the muscle can contribute to that. But the direct pull, if you're abducting at an angle that's right in line with your body, and it's the central packet that has the most effect. However, you can also use this anterior packet to flex the shoulder, to move it in the direction of the pointer. And to do that, you're basically pulling across the corner of the joint and adding flexion to the abduction. Now, a curious thing, though, is that in order to do that, this posterior packet has to stretch in order to follow the humerus in this direction. This part of the muscle has to stretch, and that means it has to relax. So we have this curious thing with a multipennate muscle like the deltoid. Here we have an anterior, central, and posterior packet built around, in pennate fashion, around a central tendon. But in order to contract one part, when you flex and abduct with the deltoid, you're using this and this packet and relaxing this one. That means these three different packets in the same muscle are served by multiple nerve connections. That's the only way they can respond differently to produce a body movement. Now, this large muscle is an important one, as I said, for abduction. And its single connection is right down here on the humerus, on a bone marking you're familiar with, the deltoid tuberosity. This muscle is really interesting because it's a skeletal muscle. It's under voluntary control. And it is kind of tacked down to the bones that are underneath it. But what it is really moving is not a joint, it is soft tissue. So when you take these packets of fibers, and you can see them arranged in multiple overlapping layers, you get what's called a circular muscle, an orbicularis muscle. And the name here, orbicularis, tells you it's circular. Oris tells you it circles the mouth. Now, when we relax, there are muscles attached around the lips and the angle that basically pull back to open the mouth. But when we want to close the mouth, we can't cross the opening. That closes the opening. So these orbicularis muscles are sort of like the drawstrings in sweatpants. When we relax, the opening falls open. When we contract it, it basically pulls down this circle into a smaller and smaller circle. And because of its positioning behind the lips, eventually holds the lips tight together, or even pushes the loose tissue of the lips that's in front of the muscle out in front. So this pursing of the lips is produced when you contract the orbicularis oris, which is behind the soft tissue of this skin and lip. So that fishy mouth, that kissy mouth, is produced by contracting the orbicularis oris. Now, the idea of an antagonist is well illustrated here because there are muscles that run to the maxilla, to the zygomatic, to the and down to the mandible in various locations to allow us to spread our mouth, pull it open these ways, lift our upper lip, depress our lower lip. Multiple muscles pull the mouth and the lips open. And this is one of the reasons that we put so much store in observing the face. There are so many muscles that we can create an impression or convey an emotion by the positioning of our mouth, or our nose, our eyes, or other parts of the face. So the idea here is lots of individual little muscles, I'll show you that in a second, that can pull together, left and right, or they can basically contract one side like the left and leave the right where it is, producing a huge amount of dexterity in the face, producing a huge amount of movement and the ability with different facial expressions to convey a mood or an emotion. Now, the skeleton and the way it moves goes back to basic mechanics. There's a fulcrum like that center part of a teeter-totter. Then there's a load. This is where a force pushes downward on the lever. And this is a applied force. You notice we're pulling the lever down in order to lift the load up. In order to lift the load, the force has to exceed, in this case, the load. But when you have those three parts, there's only really three ways you can arrange them. And just to make it simple, just imagine that the middle position is occupied by one of these three. So this first one shows a first-class lever with the fulcrum in the center. And to illustrate it, we look at the head and its nodding action. Now, this is showing a fulcrum here, and it looks like it's pointing at the mastoid process, but it is not. That's on the temporal bone. That doesn't have anything to do with mounting the skull. Back behind the mastoid process, you have the foramen magnum of the occipital lobe and the spinal cord coming down through the neck. On either side, those occipital condyles allow you to mount the occipital bone on top of the atlas. That's the fulcrum there on the occipital bone. The load is the weight of the head. You can see from this upright picture, if the fulcrum is here, most of the weight of the skull is in front of the fulcrum. So a way to test that is just relax your neck and gravity pulls your head down in a forward position. We counteract that with the muscles behind the fulcrum that attach to the occipital lobe in a rear position. And when they contract, pull the skull around the fulcrum. Now the fulcrum isn't in the center, it's well in the posterior quarter. But when you pull it down, those muscles behind act like a pull down. The fulcrum acts like a first-class lever, raising the head and holding it level. Fulcrum in the center, first-class lever. Now, I'm not that interested in you understanding and remembering the fulcrum's in the middle for a first-class lever. Just want you to see the effect of moving these three components around. In this second-class lever, the load is in the center. The fulcrum is here on one end, and the applied force is on the other. Now, this is sort of, reminds me of a wheelbarrow. If you can think of the wheel here and the load in the bucket, and you're going to grab a hold of the handles and lift up in order to put the weight here on the fulcrum. Now, to illustrate this, we have a standing foot and leg here. And if we shift our weight to the ball of our foot and use our gastrocnemius muscle in the back as a second-class lever around this ankle joint, what we do is we rise up on our tiptoes. Notice how that's kind of like a wheelbarrow. Here's the wheel. Here's the load transferred all the way down here, and we're pulling up on the handles, calcaneus in this case. So rising up on our tiptoes is using that ankle joint as a first-class or second-class lever. I should mention that this is for more than standing on your tiptoes. When we take a step, our heel comes down, we roll forward on the ball of our foot. But about the time we get to straight up with the leg, then everything that the hip and the knee and the ankle can do to lengthen our stride has already been done. This is where we contract the gastrocnemius and flex the foot. We basically extend the foot, using the ball of the foot as a second-class lever and extending our stride about 8 or 9 inches. So it does have a real practical use. The third-class lever gets me to a place where I can look at my favorite muscle, the biceps brachii. I really like this drawing because it illustrates the biceps as well or better than any other drawing in the book. It's a third-class lever, and the idea here is that the force is in the center between the fulcrum and the load. In this case, the load would be your hand, the weight of your arm, or whatever you have in your hand. And the fulcrum is way back here, the ulna on the humerus. You can see that right in the back. But the biceps brachii has origins up here. Notice that it doesn't attach to the humerus. It lays on the front of the humerus. But it basically attaches, this head attaches to the top of the glenoid cavity, and this head, called the short head, attaches to the coracoid process. So you're pulling against the scapula. When you shorten this muscle, you're basically going to pull the radius in this direction, the direction of the arrow. That flexes the elbow, as you see here, as the muscle shortens. So the third-class lever with the applied force in the center allows a great connection for hinge joints. Now, critical terms that we're going to apply to muscle action. The attachment points are called origin or insertion, and they represent the opposite ends of the muscle. The stable end for skeletal movement, the stable end, the end that does not move when the muscle contracts, we call the origin. It's the firm end that you're pulling against. So for the biceps brachii, that's those two heads attaching to the scapula. When I flex the elbow, notice how the shoulder doesn't move? In fact, the way the tendons up there are arranged, they actually press the humerus into the glenoid cavity, stabilizing the joint. The other end, the insertion, is the movable attachment. When I attach this muscle group, this body, I'm holding this shoulder solid with all of the surrounding muscles, and I'm allowing the elbow to move. So the insertion is on a place on the radius, a bump called the radial tuberosity. And that's what pulls that ulna upward in its joint, even though the force is being applied to the radius. And that's a very interesting thing. We mentioned how the forearm has two bones, the radius and the ulna, and the interosseous membrane locks them together. Where here's a situation where the muscle is delivering the force to the radius, but the actual flexing motion is between the ulna and the humerus. We describe actions of muscles with three terms: a prime mover or agonist. That's the principal action of the muscle. The principal action of the biceps brachii is to flex the elbow. It does have the ability to have an effect on the shoulder since it also crosses that joint. However, that's a minor part of what it can accomplish. Its main action is on the elbow. Another muscle, not the biceps brachii, but another muscle in that region, if it helps flex the elbow, we call it a synergist. It's another muscle that helps with the motion in the same direction. We would say muscle X is a synergist for elbow flexion. So we would say the biceps brachii is the prime mover or agonist for flexing the elbow. The brachialis is a synergist that can also apply force to flexing the elbow. Now, when we flex the elbow, the muscles that cross the posterior part of the joint must be relaxed. And the force of the biceps contraction is stretching it out. So that opposing muscle we would call an antagonist. It's on the other side of the joint, and if flexed, it will oppose the motion of the muscle we're thinking about. So if we're thinking about the biceps brachii, a synergist is the brachialis or the brachioradialis. The antagonist is the triceps brachii, and it's the main mover, the prime mover for elbow extension. So it's the one that pulls our forearm back to a straight position. We would say muscle Y is an antagonist to elbow flexion in this case. So here's the first of 4 figures that illustrate the positions and the interplay of the superficial muscles. If you take off the skin and the outer membrane, the cutaneous membrane, these are the muscles that are exposed. Things you notice right away is there's a lot of red, those are the bodies of the muscles, but also a lot of white. That's connective tissue rich in collagen. Sometimes that is a continuous connective fiber like this linea alba, a white line that crosses the soft part of our abdomen, extends to the tendons and ligaments of the sternum, and then basically all the way up the clavicle. When we see the body, we see that superficial muscles are often the largest in the body, in this case, laying on the surface. So if you are working hard to increase your muscle mass, they basically have space to grow by just bulging out under the skin. The definition between actual contractile tissue is shown here, and the connective tissue that sometimes divides them gives definition to the muscle group. So the so-called six-pack abdomen results from the fact that this rectus abdominis muscle is divided into these packets by connective tissue. Looking here at the surface, the anterior and superior quarter of the body, we get the front part of the axial skeleton and the appendages of the pectoral girdle. Here's the biceps brachii in its prominent position. The deltoid and the pectoralis major are prominent here in the front of the trunk. Down below on the anterior surface, we can see the emergence. There are places, such as the rim here of the ilium and the pubic symphysis, where the bone is right under the skin. That is enforced by the presence of very strong connective tissue. So since we run a strong ligament from the ilium to the pubis, that remains a surface feature that generally is directly under the skin. Here is the lower limbs showing that as a joint becomes more and more mobile, there's more and more dexterity and need to move. Typically, the body of the muscle is further away from the joint as it is actually moving. So in this picture, we have very strong muscles here in the pelvic region and in the thigh that are there for propelling the body at maximum speed. But as we get down here below, we notice there's a lot of muscle right below the knee, then only connective tissue as the principal tissue that connects with and wraps the connections of the ankle and foot. So we expect the foot to pivot instantly when it hits uneven ground, when it steps in a hole or steps on a stick. It has to land at different angles, but still support the weight of the body as it comes down. So there's a lot of dexterity built in here, but the actual muscle body is up here above, closer to the knee. These particular muscles, we mentioned the rectus femoris. Here it is pulling straight with the kneecap suspended in its quadriceps tendon, pulling straight on the tibia below it. We also see something rather remarkable. Look at this muscle, the sartorius, that goes from the ilial crest there on the pelvis at an angle across the thigh and attaches to the medial surface of the knee by forming strong connections with the medial bumps on the femur. Now, when we see a muscle cross the plane of the limb, we know that its main job is going to be rotation. So how is it we would use this ball and socket joint here at the femur in the acetabulum of the pelvis to rotate this foot in the lateral direction? So to point this left toe in the left direction, we would contract the sartorius muscle right here, and it is arranged, these joints are held so that we don't basically pull this directly up this line. The only way it can move is for the ball to rotate. So in rotating the femur, it rotates the tibia below it and rotates that foot in a lateral direction. So this is something you can see just by looking. Notice how the mobile joints also have obvious, conspicuous development of connective tissue. These are tendons. If they attach to a muscle below here, there are many, many ligaments which are attaching bone to bone to hold those mobile joints together. Now that's the second of four figures. Here are the large muscles of the neck and back. Notice how extensive they are, and notice that size means that they are among the stronger muscles in the body. Here is the posterior packet of the deltoid that we mentioned, blending into this medial packet that goes over the top of the joint. You can see here how it connects to the spine of the scapula. A couple of curious things here. Some places where the body of the muscle is not present, it's completely covered with connective tissue, like these connective tendons here. Also, muscles are so large. This muscle that's kite-shaped here is the trapezius muscle. And the trapezius begins its attachment at the base of the occipital lobe, and basically its origin is right down the spinous processes all the way to the beginning of the lumbar region. The spine and the base of the skull are right here in the center, are fixed points, but all the others are movable, and you'll notice it basically triangulates kind of on the spine of the scapula. The trapezius actually, let me see if I can illustrate this, is visible here in the front of the body, wrapping around this central line. You did a central coronal section. The front half would have the bottom part of the trapezius. So you can see the trapezius can actually lift on the clavicle here. So let's go back to the posterior and see the majority of that muscle. The trapezius is in a position to pull this scapula toward or stabilize it in its position by pulling against the spine, but it's also in a position to pull down on the occipital lobe or up on the scapula. Notice how if you contract these trapezial muscles, it's going to lift that scapula in this direction. These would pull it toward the spine, but these fibers down here would pull the scapula down. It would depress it down toward the lumbar vertebra. So this is another example, like the deltoid, of a great big fan-shaped muscle that is capable of moving the bone in several different directions. What did I say about the deltoid? Moving the same insertion in multiple directions means there has to be different nerves associated with the innervation of this muscle from lumbar up to occipital regions. You can kind of see a window, the big latissimus dorsal muscle, which is a lower back connection overlapping lower thorax and lumbar all the way down to the sacrum, but then basically converging on a connection on the humerus. So I mentioned the pectoralis major on the front as a major muscle for flexing the humerus because of its connection in the front. In the back, the latissimus dorsi is stretched when we flex that humerus. When we relax the pectoralis major and contract the latissimus dorsi, it extends and hyperextends. It can pull this muscle this bone way back in the hyperextended direction. And the reason for that is the joint is up here and the connection is below it. Now, when I abduct my shoulder with the deltoid, I stretch the latissimus, and I can strongly adduct by contracting the latissimus to pull it down. The final motion for the pectoralis major is to supinate the hand. And the attachment on the latissimus dorsal, now it depends on whether you're attaching it to the lateral or medial surface. Its attachment to the medial surface allows you to apply force to medial rotation or pronation of the hand. So even in discussing one muscle, Around a mobile joint, that muscle is interacting with many, many other muscles to produce this sort of relay race. And I say relay race because a relay race, you have multiple runners and you have to hand the baton off to keep the race going. Well, when I do this circumduction of the shoulder, I'm just keeping the elbow out of the way, but it's the shoulder motion. It looks continuous, but I begin that by hyperextending and abducting and flexing and adducting, and finally adducting and extending. That means different muscle groups are passing the contraction all around that joint in order to produce that continuous motion. The attachments allow for that sequence of contraction, but most important, I would say, the innervation, the nerve connections, allow for a kind of a seamless contraction of one muscle, which begins as a small contraction, raises in its intensity and force until it passes the central point of its effectiveness, and then a decrease in contraction as the next muscle on the other side takes up sustaining that motion. The lower posterior view shows some of the more powerful muscles in the body, the buttocks, the thighs, and the lower legs are full of large muscles because our lower limbs support our stance and our locomotion. So these have to be very powerful in pushing to propel us forward. And you can see that the position of these hamstring muscles is to cross the knee and flex the knee during that process of walking or running. So what would we have to do to take a step? We would have to hyperextend. If we reach out, let's reach out with our right leg and put our foot down. Now we have to extend the hip and hyperextend the hip as we're rolling our weight over that leg, foot on the ground. We then flex the knee. We're going to flex the knee at first and then extend the knee to push off. We're going to, when we reach, flex the foot and then extend the foot to push off. And then as the foot comes free of the ground, we notice a great flexion of the knee. Often in a good runner, the heel will rotate up and touch the back of the leg as you swing it forward. So those four figures that we've just covered are a good sampling of these superficial muscles and be able to identify these major muscles by name and position. After that introduction, we're going to be looking at a sequence of specific muscles. These muscles are going to be interesting in the way they interact with all the other muscles in the packet, but you should pay a special attention to those that are going to appear on Wednesday on that list of 10, the worksheet muscles. So, as you would expect, I will start with my favorite muscle, the biceps brachii. The name biceps, bi means two, and ceps comes from cephalo, meaning head, two heads. When we talk about heads and muscles, we're typically talking about origins. And here is that Y-shaped top. A long head, you can see in the lateral position, coming up, going between the greater and lesser tubercle and being tied down by ligaments to hold it. There's a groove there called the Intertubercular Groove, and the tendon runs around it in a 90-degree angle, just like a belt in a pulley. That transforms it into a horizontal orientation, and it crosses the joint to the top of the glenoid cavity. You cannot see it, but just about in this position. The collagen of the tendon binds continuously with the collagen of the periosteum of the scapula. And that periosteum is bound to the collagen that embeds in the bone. So when we contract this muscle, it basically places force in the lateral direction on the head of the humerus and pushes it into the glenoid cavity, stabilizing the joint. The second head, the so-called short head, crosses over on the anterior surface and attaches to the coracoid process of the scapula, a much more forward and exposed attachment. Now these two are still a parallel muscle, and when they contract, they're going to pull against this motionless origin and shorten in this direction. In this case, we're kind of obscuring the main tendon of the biceps. It buries itself under these flexors and under the pronator muscle. It crosses, see that angle there? You're going to expect the pronator is going to produce a rotation, and the name tells you that's right. Pronation means that it's going to medially rotate this joint. So this tendon, the lower one, going to bury itself in here and attach itself to the lateral bone. The radius is on this side. The ulna is over here. And the biceps is going to attach to the radial tuberosity about in this position. Its main action, flex the elbow. Later on, we may expose underneath it the brachialis, and over here, crossing the elbow. Now the brachioradialis goes from the humerus all the way down here to the base of the radius and the wrist. But because it crosses the elbow, the brachioradialis and the brachialis can provide synergistic support for flexing the elbow. The front of the thorax, here's the biceps brachii again. And the biceps brachii, you'll notice, tucks under the deltoid, which comes to here, and the pectoralis major that spans the entire superficial aspect of the mammary region. Notice the broad attachment of both of these upper muscles. We will find that from the costal cartilage down below, the pectoralis major goes up the sternum, clear past the manubrium to the clavicle and about 2/3 of the clavicle. Look at that very broad base of attachment. So multiple angles of fibers are going to be presented to and pull on this humerus. The deltoid, we can only see the anterior attachment, the lateral 1/3 of the clavicle, and then beginning with the acromion, going around the acromion and directly down the spine of the scapula. So a big U-shaped connection in order to produce the origin of the deltoid. Look at its position. It's draped over the top of that humeral glenoid connection. So its natural activity is going to be to rotate that ball and socket in a lateral direction or abduct the arm. When we spin that figure around and look at the posterior aspect of this shoulder region, we see how the deltoid completes. See how it from the acromion, it extends all the way around this lateral edge of the spine of the scapula. From here, you can kind of see that these fibers that are kind of going directly over are going to be great for that lateral abduction, straight away from the body in the midline. But if we want to abduct and also move this humerus in a posterior direction, so from the anatomical position, if I want to abduct and move the humerus in that direction, see how I'm hyperextending the humerus, then significant force can be applied by this posterior packet of the deltoid. So this kind of shows the complex action. Right below and peeking out here are the bodies of the Triceps Brachii, because we're now on the posterior surface. This tendon is going to extend downward across the elbow and attach to a bump of the olecranon. That's its only insertion. And so when I flex my elbow, I stretch that muscle, the triceps. When I flex the triceps or contract the triceps, I basically pull it back toward a position closer to the shoulder and extend the elbow. Now the large muscles that we mentioned, the deltoid and triceps here, the trapezius is shown here. So you can basically pull in both directions. You're not going to pull the spine into a curve or move the spine in this direction. So this is the origin. The insertion will be the parts that will move, which will be the spine of the scapula, moving the scapula medially, moving it inferiorly. Using these, we can move it superiorly. And if we go around to that front aspect again, we can use it to move, basically pull the scapula slightly anteriorly. This window here shows the base of the scapula and how covered with muscles it is. The scapula is a mobile bone. Its only connection to the skeleton is that acromioclavicular joint and the joint that hangs the arm. So this is suspended by soft tissue. Muscle is soft tissue. And this heavy musculature is needed to move and to position the scapula for the various uses of shoulder, arm, and back that are possible in the human skeleton. Here's an unusual muscle because it doesn't cross a bony joint. If you can look at that white, basically boomerang-shaped structure in the center. This is the central tendon. This is all connective tissue, and it forms the upper crown of a dome. Now, the central tendon is not contractile. It basically just ties it all together. So if you can think of this, this reminds me of a trampoline in reverse. Here is the part you bounce on, and here are the springs. But in this case, the springs are going to arch downward and connect to the very bottom rim of the ribs on this side. So here and here, these are arching downward to a very deep connection. Around the back, it's going to attach to the ribs and across here, of course, down in some places to the vertebral column. So this dome sits like this with a high center. And when you contract the muscles, the body of the diaphragm, it basically pulls that central tendon downward. Now, when it does, it increases the volume of our lungs, which basically forces air down our airway and into our lungs. This is how we inhale. The diaphragm is large enough and the lungs have a large enough capacity that at rest, like we are now, a very, very quiet breathing supplies all the oxygen we need to maintain our alertness and our learning, our understanding, and for one of us, the ability to actively manage that airflow so that I can also talk and lecture. This diaphragm, you'll notice, forms a floor. This is taken from the upper side, and this is where we are looking down. We are looking at the from the thorax to the wall that separates the thorax from the abdomen. However, several important things have to cross the boundary. And so here we have the thoracic aorta, the descending aorta with its attachment. It's basically attached firmly around the spinal column at this position. Here is the esophagus, which is a tube that only opens up when you swallow. Most time it goes through a fixed perforation in the diaphragm. As we breathe, the diaphragm has to slide up and down on the esophagus. Over here, here's the inferior vena cava, returning blood from below the diaphragm and from the entire abdomen, pelvis, legs, and feet. Flowing up means that it has to have a permanent perforation, in this case the central tendon. And again, when we depress this as the floor of the thorax, has to slide up and down on this inferior vena cava. Now, for quiet breathing, the diaphragm is sufficient. If we do mild exercise, like let's do a fast walk, so our breathing increases a little bit, mostly the diaphragm can move faster and move further and handle most of those oxygen needs. However, if we really start jogging or running, let's say we're doing a 10K for time, and our oxygen demand is going to go high, and our diaphragm is going to be working at maximum capacity, being pulled way down to the bottom of the rib cage and being returned way, way up during exhale. But at that point, we actually get more lung capacity by moving our rib cage, and it is these muscles between the ribs called the intercostals that kick in during active breathing. Here's something where we're going to, during active breathing, we're not going to just relax and let the air trickle out by the natural recovery of elastic tissue. We want to force that air out so we can take another quick inhale. So we have muscles that basically rotate the ribs up and out, and muscles that pull the ribs actively back down, expressing that air out, getting rid of it so we can take our next breath. So for quiet breathing, this diaphragm is just fine. But for active breathing, we're going to use the diaphragm still at maximum rate and depth of contraction. We're going to add these intercostal muscles. Here you can see the internals and the externals, named as different muscle groups because the externals lift the rib cage up for an active deep breath, and the internals bring it back down. Here's a posterior view of the arm showing the superficial layer of muscles. Here is a good shot of the shoulder showing you a ligament. See how the head of the humerus is bound to this particular ridge here on the scapula, stabilizing this joint from the posterior side. The Triceps Brachii cannot be fully appreciated from this shot because the long head of the triceps crosses over and attaches to the scapula. The lateral head attaches here high on the humerus. These are two of the three origins. The medial head is a very short head, and it attaches on an intermediate position, a little below the attachment of the lateral head. Three heads pulling against three attachment points. And when the bodies contract, they take this tendon, the insertion tendon, and pull on the exposed olecranon of the ulna. So if you can imagine taking this picture and flexing the elbow so you no longer see the lower arm, you can see that as it pivots around this joint, you're going to pull this tendon around that corner and make it longer. So as you flex the elbow, you're extending the length of the triceps, and it is relaxed. To return your arm to this position, you would contract the Triceps Brachii, pulling that olecranon closer and closer to the posterior shoulder and straightening or extending the elbow. When we look at a view of the foot, we see an organ that is mainly important for its ability to move. So we have to adjust to uneven ground, and the more we can flex the foot and the ankle, the more powerful and speedy our walking and running. So we see lots and lots of tendons. These tendons are coming from muscles that are high in the calf and that basically run like cables down around the various bone markings to their insertion. So this is actually a combined tendon. Notice it's splitting into 4 parts, and notice the name, the Flexor Digitorum Longus. The digitorum is what it acts on. The digits are the toes. Flexor tells you what they do. So from the anatomical position, when you do the flexor digitorum, flexing is moving the toes downward. And longus basically describes the shape of the muscle. So you'll notice that it runs around that medial malleolus, that bump that's produced by the tibia on the medial side. And it catches on that. It's held there by another ligament. So this acts as a pulley. When you flex the muscle in the calf, it pulls this way on the toes, exerting force on the surface of the ground. As is true in the thumb, in the hand, there is often special connection for the great digit, the thumb in the hand and the big toe in the foot. This is the flexor hallucis longus, same approach to the name, but hallucis refers to the big toe. Now, where there are intrinsic muscles, it is important to realize that these smaller muscles that are actually in the foot are small enough that they don't interfere with the dexterity or the power of the transfer of the bigger muscles in walking, running, jumping, and so forth that are high above. But they are important in maintaining the position of the bones one to the other. So here you're going to have 7 carpals, 5 metacarpals, and 14 phalanges that you have to keep in line in order to form a functional foot. So that's just part of what you can see. Notice how there's almost no muscle from this distal region of the metatarsals. You can kind of see 1, 2, 3, 4, 5 right here as you look past those tendons and muscles. And mostly just ligament sheaths and tendons activating and moving the toes. Now, we've talked mostly about superficial muscles and haven't done very many dissections, but where there's a need for a lot of muscular power, we often find a superficial layer operating above an intermediate layer, which is operating above a deep layer, often right up against the bones. And this is showing the posterior view of the right leg and foot. This is shown in a foot extended or tiptoe position. And we have also removed the superficial muscles. Do you see this cut edge where the gastrocnemius, which forms that bulge on the calf, the profile of the skin shows you where the gastrocnemius would be, and it will completely cover up these deep muscles. The deep muscles, you'll notice, are layered, so they're often smaller. They often extend, and they do extend, notice, all the way up to the top of the femur, top of the tibia and fibula and make use of all of these bone regions to establish connections. So the flexor hallucis longus, that controls the big toe and its flexing, is this muscle right here, attaching high up on the fibula. The flexor digitorum longus, you'll notice, is on the other side of the tibia, the medial side, and it attaches high up on the tibia. But they go through the same wrap ligament that holds them down in a pulley-like fashion, so that when the foot is flat on the ground, this is a 90-degree angle, it basically can pull around a corner. If you're standing there and you're maintaining your upright posture by pressing down with your toes, the contraction is occurring up here, but the force is pulling along the surface of the floor as you press your toes down to exert the balancing force that is needed. Remove some of these, and you see even deeper muscles. The Tibialis Posterior, you'll notice, bridges its attachments between the tibia, the fibula, and forming the Tibialis Posterior then is going to basically cross out of this complex in order to produce its principal motion. This is a curious muscle and one of my favorites. We're all accustomed to the excellent performance of our eye, and that contains lots of external and internal muscles. These are the external muscles in the orbit, that cavity that is formed by 7 bones of the skull and forms a smooth, bony socket to suspend this eyeball with its clear lens and its clear cornea pointed directly at the world. Now, in addition to moving our head to direct our vision, we can move our eyeballs within the socket. And that's the main purpose of the muscles that you see here. The 4 straight muscles, called rectus muscles, are named based on their position. This is the right eye. So this is the lateral rectus, attaching from back here where there's a hole for the optic nerve to go out of. But from the connective tissue that's around that hole, the lateral rectus attaches here to the lateral side of the eye. If you shorten that, you can kind of see that you would rotate the eye and its iris in the lateral direction. The superior and inferior rectus muscles basically show the same kind of analysis. If you contract the superior, you're going to rotate the eyeball up. Contract the inferior, rotate the lens and the opening downward, and in a position you can't see because it's covered up. There is a medial rectus running right to the other side of the eye that would basically direct the eyeball in the medial direction. So that's pretty much for the straight movements, up, down, left, and right. But there are 2 additional muscles shown here. From the medial edge, the inferior oblique comes across the eyeball at an angle, and you can see it attaches to this spherical eyeball on the posterior and lateral surface. In fact, its attachment is under this lateral rectus. So when it pulls, it doesn't pull straight, it pulls at an angle. So since we're pulling medially and posteriorly, it will rotate the eyeball laterally and anterior. This is the one I want you to look at, though, because it's on your list. The superior oblique. It does something that is even more remarkable. All of these muscles, other than the inferior oblique, attach over here, the back of the eye. This one runs forward. This little loop called the ligamentous sling. It acts like a pulley. Notice how the tendon of this muscle goes through this loop and reverses direction. So in the superior oblique crosses the eyeball at an angle and attaches to this superior and lateral surface. So when you pull in the medial direction, you're basically going to rotate this medially. And when you rotate it from the superior attachment, you're going to basically rotate the eyeball down. But the thing that amazes me about this is how it got this arrangement with a sling. How does it change that direction? I can pretty well see how a muscle attached to the eye could have variation in attachment, and the one that pulls the eye laterally the best is the one where the genes are preserved. But I don't know how you make a sling and pulley arrangement out of this superior oblique. Now, when you take the eyeball itself out, you can see the attachment back here by the fissure. See the sutures that are forming the tight connections between these bones. And here we have it, the frontal bone right here, the zygomatic bone out here, the maxilla down below. We're seeing parts of the sphenoid and parts of the lacrimal bone. But down here at the back is a hole where the optic nerve, the nerves from the retinal cells themselves, go out. And all around that, here's the superior and inferior rectus muscle attachment. Here's the lateral and medial rectus. Here's the inferior oblique. It's been cut before it shows its attachment up here on the eyeball. And here's the superior oblique from the back of the eye forward through that sling, reversing direction and coming back and attaching to the top of the eye. So as a result, we have I remember when we went from seats that went back and forward to seats that could go in 6 directions, we have a 6-way directional control of our eyeball, which explains why it can adapt to sounds and check out flashes and move so quickly in our head to exactly what we want to look at. This is a full shot of the face. And wherever you see this kind of pattern, lots and lots of different muscles, it means lots of different movements. Because these are small muscles, you're often moving something like the corner of the mouth up. That would see how this zygomaticus major would move the corner of the mouth up, and how this particular muscle here, the depressor, Anguli oris. Look at that name. Depressor means what? It pulls it down. Anguli means the angle of the mouth, and oris means the mouth. So the name tells you what it does. It pulls the corner of the mouth down. But right next to it, notice that there's a depressor labii inferioris, meaning pull down the lower lip. And so we have fine control of the different regions of the lips to provide multiple shapes, multiple movements. That's why we say this face is so mobile, so expressive. And it's the multiple muscles in the face that produce that phenomenon. Now, one very, very prominent feature of looking at the face and the superficial muscles are these orbicularis muscles. The circular muscles that surround the eye allow us to pinch down the skin that surrounds the eye and basically reduce the opening. Now, these are in addition to the muscles that close the eyelids. But the same idea as the mouth applies here. These circular muscles are going to basically take this outer perimeter and squeeze it down right around the opening. Same thing here with the Orbicularis oris. Again, the names are telling you a great deal about the either the function or the position or the shape of the muscle. Down to the posterior view of the calf, And we can see what we will call ankle extensors. The main muscles shown here are attached high up, sometimes crossing the knee and actually attaching to the femur, but traversing the entire tibia and fibula region. This is the gastrocnemius that we spoke of, this muscle with two heads, gigantic heads, and heads that converge on this central tendon. Now, here's where your terminology is coming to help. Your calcaneal tendon is the tendon that attaches the gastrocnemius to the calcaneus, the heel bone. That's why when you contract this muscle, pulling the calcaneus toward the origin, you're basically, in a complex way, you're balancing on the ball of your foot and you step up on your tiptoes. But remove that gastrocnemius, cut it here and up here, and remove it, and underneath it, you find a whole nother layer. This muscle is the soleus. Notice its bigger wrap. You can see the soleus here around the outside portions of the calcaneal tendon. But it's a broader muscle, a thinner muscle. But as the gastrocnemius provides most of the push, most of the force, and as it gets stronger and stronger, it can bulge out against the skin. The thinner soleus is the muscle with multiple fibers and fascicles from multiple directions that allow you to pull on the tendon and to pull on the bones of the foot to adjust left and right positioning. Now, we walk on two legs. Balancing on two legs is not an easy task. And so it is fine adjustments over the surface of this soleus. Your foot hits wrong, it's at a tilt. Your balance is off. It is the soleus that contracts and pulls this tibia laterally or medially to maintain your balance. The popliteus. The popliteal region was the back of the knee, and so the popliteus is appropriately named. But you'll notice the way it wraps from the medial edge of the tibia at an angle all the way around to the lateral edge of the femur. That can only mean one thing, and that is rotating the knee joint. So in addition to the rotation you can get at the hip from the Sartorius, the popliteus can rotate the femur on the tibia and produce additional lateral rotation. The anterior view before, we looked at the biceps, deltoid, and pectoralis major, but we didn't look very much at this lower abdominal wall. We can see a number of muscles that are below these more prominent outer ones. The serratus anterior produces that sawtooth muscle on the left and right, right under the arm when well defined. We also see a number of muscular sheets that are running at different angles. And when we tense them all, we reinforce the soft front of this abdomen. The rib cage is curling down in this position and supporting the thorax, but the abdomen is supported by soft tissue. So the internal obliques, you'll notice, are running almost horizontally around the body. The rectus abdominis is at right angles to that. And around here, another layer called the external obliques have been cut away. You'll notice that they run at an angle down from lateral and superior to medial and, lateral and superior to medial and inferior. Placing these sheets at different angles means that when you contract them, it provides a very solid muscle wall, supporting the integrity of that abdominal cavity and all the organs within. Muscles that move the leg are shown here, and I've gone an hour and a half already. So what I'm going to do is go to end the show for just a moment. Stop that recording.